closer estimate. We could choose the distribution of points. By the behavior of rho of x, y, z. Actually x, y, 0, or x, y, any z, right? There's no z dependence. So we could plot this as a surface in three-dimensional space. And use the shape to choose sample points. Where this function is relatively flat, it's not changing by much, so we don't need to choose as many points in that region, okay? So, for example, in the three-dimensional region, okay, where now this is x, and this is y, well, x is in this direction, the x-axis is down here, and the y-axis is over there, right? There might be parts of this region where the graph is reasonably flat. If we do extend this graph up into 3 dimensions, meaning that this density function is not changing very quickly, so we don't need a whole lot of sample points in that region. In the regions where this thing is changing very rapidly, we need more sample points, right? And we're not going to analyze that. I'm just referring to that as something that fits into everything we're doing with these functions, okay? So, actually analyzing it like that comes somewhat later. But still, I want you to have that idea. Does that make any sense? Okay. Well, maybe, maybe not, but kind of store it away, okay? Now, we're not going to do this. We're just going to set up an integral to find the average density. Okay? But sometimes you have a function you can't integrate. We can integrate this. Okay? We can do this definite integral. Okay, so we just set up an integral.